Okay, so what we're going to do right now is kind of introduce some of the thermodynamics of two-component solutions. I gave you an image a couple lectures ago of the pressure versus composition diagram for a system that obeys, a system where the solvent and the solute both obey Raoult's law. And I kind of went over that really quickly. We're going to go over it in a little bit more depth today to look at where that diagram came from and what it tells us. And then we're going to use that diagram to generate a different kind of diagram that will be more useful in looking at fractional distillation and things like this. So, first of all, it's remind ourselves of what the situation is that we're talking about. We are referring in the rest of this conversation to a two-component system in which the vapor is able to reach equilibrium with the liquid, right? And so we looked at how this happens for pure systems and for components where you have a mixture of two compounds. In general, when you've got the potential to form gaseous products, liquid state, or solid state, you can always reach some equilibrium between those three different states of matter. Right now, we're only considering ourselves with the equilibrium between a liquid solution, so it's some solute dissolved in some solvent, and the vapor above that solution. Now, when we refer to systems obeying Raoult's law, we're talking, when I say that in this context, I'm talking about the whole, the entirety of the system obeying Raoult's law. So Raoult's law was the pressure of the component when it's in the solution is equal to the pressure that it has when it's the pure component times its mole fraction in the solution. And so we're saying that the pressure of either component, the solute or the solvent in this liquid, the pressure of those components in the vapor above the liquid is proportional to their pressure when they're pure substance times their mole fraction in this actual scenario. It's possible to not have a system where both components exist in the vapor phase. There are things that are referred to as non-volatile solvent or solutes, and those are solutes that they're bound so tightly to the liquid phase that they never enter the gas phase at all. In general, a system like that, the solvent will exist in the vapor, but the solute itself will stay bound to the liquid. That is not the kind of system that we're talking about right now. The kind of system that we're talking about right now is the kind of system where both the solvent and the solute exist in the vapor above the solution, and both the solvent and the solvent obey Raoult's law. Now, remember, we've already said that in general, it's not very safe to assume that a solute is going to obey Raoult's law. That's why we have Henry's law, because the solute is the species that's has the lowest number, and so the interactions that it feels in the solution are very different than the interactions that it feels in the pure substance. But we're going to address the situation where Henry's law doesn't obey. In this instance, the strengths and types of the interactions between the solvent and the solute molecules are very similar in size and magnitude. The interactions are similar in strength, size, and magnitude to the interactions between two solute particles or two solvent particles. And so essentially what we're saying is that there's no change in the electrical potential when you go from being the pure substance to being the substance in solution. So this is the point I want to drive home. So this gets back to potential energy. So let's say we've got A species and B species. And you've got a pure substance over here filled with A species. And you've got some pure substance B over here. And all of these are little spherical molecules or ions or whatever they are. and they're attracted to each other by their electrostatic attractions, right? And there's some certain like strength that an A molecule acts on another A molecule with, and there's some certain strength that a B molecule acts on another B molecule. If the strength with which the B molecules interact with each other and the A molecules interact with each other is the same exact strength with which an A and a B molecule interact electrostatically, then we would invest energy in pulling an A molecule away from other A molecules, right? Because anytime there's an electric force, it takes energy to separate them. And then we would get energy back when that A molecule came in and started interacting with B molecules. For the ideal solutions, the amount of energy that's required to separate two A molecules is the same exact amount of energy that is released when an A molecule associates with a B molecule. And so there's no energetic cost for going from this state to this state for these ideal solutions. Not all solutions are ideal, and in general there is an energetic cost because those interactions won't be identical. In the absence of a change in this like electrical potential, all mixing can be described by entropy effects. So if there's no electric force driving the dissolution of one system into another, then it must be the entropy effects, the increasing disorder, that drives that reaction. So again, we're talking about systems where A and B interactions are analogous in both size and strength, or magnitude of interaction, strength and type of interaction is the better way to say that. So that is that fun. So, doing a little math, just a really quick bit of math, we can express the pressure of the vapor in terms of the mole fractions of the components and the pressure of each component when it's in the pure liquid. It looks something like this. We start off and we say that the pressure, the total pressure in the vapor is the pressure of the solvent plus the pressure of the solute. Both of these guys obey Raoult's law, and so the pressure of the solvent is the mole fraction of the solvent times the pressure of the solvent in the pure system. So I kind of used a different notation in this set of notes than I used in the last one. But when I put P pure solvent, that means that I'm saying if you have a pure liquid solvent, what's the vapor pressure above that solvent? So pressure of the solvent is the mole fraction of the solvent in the solution times the pressure of the pure solvent. You have to add to that the pressure of the solute. The pressure of the solute is the mole fraction of the solute in that particular solution times the pressure of the pure solute. Again, both of these guys are obeying Raoult's law. We can express the mole fraction of, if we just call these components A and B, we can express the mole fraction of any one component in terms of the mole fraction of the other. If we're talking about a species B, then its mole fraction is just 1 minus whatever the mole fraction of A is, right? If you got a two-component system, then both the mole fractions have to add together to 1. And so you can express XB as 1 minus XA. If you rewrite this out, you call one component A, its pressure is XA times the pressure of the pure. This guy is 1 minus XA times the pressure of the pure. You end up with a term that looks like that guy right here. And that simplifies to this term here, where we can say that the total pressure above a system, an ideal system, total vapor pressure above an ideal system, is the pressure of component B, if it's pure, plus this term that has the mole fraction of A times the pressure of A minus the pressure of B. And you'll notice that this is y equals mx plus b form, right? Y is equal to slope times, or sorry, slope right here times whatever the x value is, and b is your, or this guy right there should be your slope-intercept. And so it seems natural that we could generate a graph that gives this same information, and we'll look at such a graph right now. So that was this guy right here. You'll find in your text, it's the expresses the pressure, the total pressure in terms of the mole fraction of a component. It doesn't matter which component you chose. It's good to know that in one, whatever the shape of the graph is, if you're expressing the mole fraction of one component, if you express it instead of in terms of the mole fraction of the other component, it'll be inversed. We're looking here at a system of benzene and dichloroethane. So on the x-axis, we're tracking the mole fraction of dichloroethane as it moves from 0 to 1. And you'll notice that when the mole fraction of dichloroethane is at 0, we're calling dichloroethane the A component, it's the one we're tracking on the A-axis, that the pressure of the system is just whatever pressure the pure benzene has, right? If the mole fraction of the dichloroethane is 0, then we've got pure benzene, and so we expect the vapor pressure to be the vapor pressure of the pure benzene. And that gets borne out in the equation. If XA is 0, then P total is P of component B, right? Similarly, if we go over here to the opposite end of the spectrum, where the mole fraction of dichloroethane is 1, then the vapor pressure is going to be PAP, right? And so that's natural. You go all the way to the other extreme, where we got only component A, then you're going to have to whatever the vapor pressure of that system is when it's in its pure form. And notice that these two lines that make an X, these express the partial pressures of each component, and the total pressure is simply the sum of the two partial pressures. And we get that linear relationship that's predicted by our little mathematical expression there for the total pressure. Right? That is the pressure as the function of the mole fraction in a two-component solution that behaves ideally. Right? This is a very limited graph in that it only works for some systems. Benzene and dichloroethane happen to deviate very, very smallly, or in only a small magnitude, to the ideal behavior. And so this kind of a graph works very well for those two systems. And the reason for that is that we're dealing with, it's 1,2-dichloroethane, so it's overall it's not a very polar molecule mixed in with benzene. So we've got two non-polar molecules that interact mostly through dispersion forces, and so we're getting to that situation where we can approximate that the magnitudes of these interactions are equal. We've got that ideal system. I think I showed you in your lecture notes from a previous lecture that many systems do not behave this way, and you'll get bulges or dips in the total pressure. So this line will actually curve this way or that way, and some of these partial pressure lines move around and they don't behave with that linear relationship. So pay attention to this coming argument, because this is not something that that your book discusses. So your only frame of reference for this next piece of discussion is going to be the notes and whatever your ears pick up. Graph right here that we're looking at gives pressure as a function of the mole fraction of a component in the liquid. We can just as readily create a graph that shows the pressure as a function of the mole fraction of that component in the gas phase. And that's gonna be very useful to us. So we're gonna have to grind out a little bit of math. We want a term for the mole fraction of the component in the gas phase. We're going to change our notation. We were using XA for the liquid phase mole fraction. We'll use YA for the gas phase mole fraction. And by Dalton's law of partial pressures, the gas phase mole fraction is simply the pressure of the partial pressure of that component divided by the total pressure, right? Does that make sense? Bernoulli's law, gases, pressure is proportional number of moles, and so the mole fraction is going to be number of moles of A in the gas phase divided by total number of moles in the gas phase, but pressure is proportional number of moles, and so we can just use that ratio, the two pressures. And we write an expression for PA. Again, A is behaving ideally, so it's the mole fraction times the pressure of the pure. The total pressure just comes from our equation up here, PV plus XA times PA minus PV, right? We're going to take this equation and we're going to rearrange it, and we're going to solve for X, or XA, and we get this big term here, XA, in terms of PA, PV, and YA. And now we plug this term right here that we solved for XA back into that spot, and we do a little bit of manipulation. I'm not going to tell you what the manipulation is because I think I might ask you to do this as one of your exam problems. You do some manipulation, and you get an expression that looks like this for the total pressure of the component in the gas phase. In terms of, the total pressure in the gas phase in terms of the mole fraction of that component in the gas phase, in terms of Y. So, real quick check to look at. First of all, you don't see this linear relationship. We didn't have Y as a direct multiplier in the numerator. It's showing up here in the denominator. So that's leading to a curvature of this pressure versus composition curve. Check to see that it obeys the expected behavior in the appropriate limits. If we go to YA is equal to 1, then this is PA minus PA plus PV. PV over PA is PA, and we find out that this whole expression reduces to simply the pressure of component A in the pure, right? In the event that YA is at 0, this whole term goes to 0, and we got numerator divided by denominator just gives us pressure of B of the pure. And so it does the same exact, it has the same exact behavior at the limits as the last expression, but in that middle range of mole fractions, it deviates. This guy is the analogous curve for the benzene dichloroethane mixture. That's all I have to say about that slide. So you can take these two graphs and you can kind of stack them on top of each other along a common axis. Remember that XA and YA both begin at 0 and end at 1. So this should know that this is YA on that axis. You bring these two guys together and the curves stack on top of each other. The curve that separates you from the liquid phase, this is liquid up here at the top, sits at the top, and the gas phase curve, the gas phase mole fraction curve, sits there right below it. And this combined graph allows you to relate the mole fractions of species in the liquid to the mole fractions of species in the gas if you you are at the same conditions of pressure. Did I already skip the phase rule? Okay. So let's play with this thing for a second. First of all, we're going to switch our notation. Instead of plotting XA or YA on the axis, we're going to use Z average, and Z is going to indicate the average composition where both the gas phase and the liquid phase are incorporated. So you imagine the total mole fraction in the combined system is going to be a function of the mole fraction in the gas phase and the mole fraction in the liquid phase. So we switch our notation, we'll use a Z average, and let's just play with these graphs and see what they tell us. So first of all, when we look at the liquid graph, the pressure as a function of pressure as a function of the mole fraction for the species in the liquid solution, imagine that you have a liquid at some mole fraction, say this point right here, and it's at some very high pressure that brings it up above this line. What phases are available to that system when it's up here? What phase does the system exist in? So remember, this line plots the vapor pressure of the system. And if we go to a pressure that's higher than the vapor pressure, what's that? Huh? It's going to be liquid. So if we've got a system at like this mole fraction, whatever that number is here, but at a pressure way up there, then the surrounding pressure is greater than the vapor pressure of the system, and so all of that vapor gets pushed into the liquid phase, and you don't have a liquid phase, you've got a vapor phase, right? If you begin to lower the pressure, at some point, you get to the point where the external pressure and the vapor pressure are the same, and at that point, what happens? Then you have an equilibrium. You get to the point where it's now energetically favorable for these species to move off into the gas phase, right? And so, right at that line, you are at a point of equilibrium between the liquid and the gas. So you'll have in that system some liquid, some gas. The gas phase will have the gas phase mole fractions predicted by the curve on the right. The liquid phase will have the liquid phase mole fractions predicted by the curve on the left. What happens if you lower the pressure? Say we're at a point right on the line, and then we drop the pressure down to move us into this region of the graph. What state is the system going to be in? Surrounding pressure is lower than the pressure of the vapor, and so the vapor is going to do a free expansion against the external pressure. And all of the gas that's in the liquid will transfer into the vapor phase. And so you'll be in a system where you only have one phase, right? Only the vapor phase of the system still exists. Yeah? Okay, so let's do the same thing over here with this graph. So, with this guy, now we're looking at the Y mole fractions. Let's say we start at a point over here where the surrounding pressure is less than the vapor pressure in the gas. What's going to happen what state of matter is the gas going to be in if the pressure is lower than the vapor pressure? This is kind of worked out in the conversation. So we're looking at the vapor pressure in the liquid. Pick a mole fraction. Say you're at whatever this guy is, maybe right in the middle, 0.5 is your mole fraction. The pressure is lower than the external pressure on the system. So imagine that the external pressure is provided by a piston. I should have mentioned that. You've got this external pressure provided by a piston. If the external pressure is lower than the vapor pressure of the gas, indicating that you're down here, then you're going to go gas phase, right? The gas is going to expand freely, all the liquid is going to turn into gas, you'll be in only one phase, right? You can alter mole fraction and stay inside that phase. If you increase the pressure, you'll reach a point at which you intersect this line. At that point, you're going to have equilibrium between the gas and the liquid. You'll have two phases, liquid phase and the gas phase. We're just reading the graphs in kind of the same exact way, we're just looking at the different curves. The Y mole fraction curve and the X mole fraction curve, the pressure curve with respect to those mole fractions. What happens if you increase the pressure even further?
Well, it goes into neutral.
Increase the pressure even further, you move out of that equilibrium, and you end up moving into that top part where you've got liquid. So this probably important right now to talk about the degrees of freedom that different systems have. Our degrees of freedom is always according to this rule. F is equal to components minus phases plus 2, right? Here we're dealing with a two-component system, so our degrees of freedom is equal to 2 minus P plus 2 is equal to 4 minus P. So in the case that we have one phase, our degrees of freedom are going to be equal to 3, right? And the relevant variables that we're going to be concerned with are pressure, temperature, and mole fraction. Each of these graphs was plotted at one value of temperature. And temperature is one of the variables that we have. And so, if we're in the region where we have one phase, so either down here or up here, we've got 3 degrees of freedom. But we've already fixed temperature, and so that gets rid of one of our degrees of freedom. And so we only have 2 degrees of freedom. In all of these graphs, we were plotting the vapor pressure with respect to mole fraction while maintaining temperature constant at some value, like 25 degrees Celsius, whatever it is. So in the area where we have 2 degrees of freedom, one phase, we can alter the pressure or the composition and kind of stay in that region, right? If we want to be on one of these boundary lines indicate that you've got equilibrium between 2 phases. You've got a solid phase and a liquid phase. And so P is equal to 2. Our degrees of freedom is 3 minus 2 is equal to 1. And so you would expect that you can't alter both the pressure and the composition independently and maintain equilibrium. And that's what these curves are telling you. If the pressure changes, your equilibrium concentration is going to change, right? Something else that you can tell, okay, so let me draw a different picture of this. paragraph. We got XM